Welcome to the third part of causality and directed acyclic graphs. My name is Laurens Waldrop, and today we'll be talking about causal discovery algorithms. We've seen how to work with the graphs or networks, and we've seen how conditional independence relations relate to those graphs, but what we haven't seen is how you get from those probability distributions to a particular graph. So how do you discover the particular causal relations? That's what we're going to discuss today. We're going to discuss what is called the inductive causation algorithm. It is called such by Pearl, but it goes also under the same name of the PC algorithm for Peter Spiritus and Clark Glimmer. It's basically the same algorithm, and the reason we discuss this version and not others, because there are many variations, is because this idea is the basis for almost all of these kinds of algorithms. So many of them will have the rules that we discuss and others to include so that the inductive causation is better. But the basis is all the same. So we start with an example. And in the example, we basically assume that somebody, and we call this an oracle, knows what the true graph looks like. And so these algorithms are sometimes called oracle versions or oracle algorithms. And they're proofs to show that they work because there are no statistics involved. And it doesn't apply naturally to the real world, of course, where we have uncertainty and we need to invoke statistical tests, for instance, to determine whether a correlation is significant or not. But for now, to illustrate the algorithm, we will assume that we can just ask the oracle, is this a significant correlation? And the oracle will say yes or no, according to exactly the true graph. We start out with the graph that is completely empty, and we need to fill this with the edges that we see on the top left. And if we obtain the correct graph, then of course we see that it works. So what do we need to do? Well, we know from the previous parts that we can look at conditional independencies. If a conditional independence relation holds in the distribution, so in our data, then maybe we can infer this arrow to our graph. And so let's start with the connection between 3 and 5 and go through the example. And we just use the rules of conditional independence relations and put them into d-separation to put it into a graph. We start with this example and then we go to the generalized algorithm that Pearl wrote up. So we start with 3 and 5. Is there a connection between this? And how we can think of this is basically with correlations and partial correlations. So we're interested in the connection with 3, 5, and we start with the Pearson correlation between 3 and 5. So there's nothing partialed out, it's just a simple correlation between two variables. And we ask the oracle, is there a correlation between 3 and 5? The oracle looks towards the true graph, which is there, and says, true, there is a significant correlation between 3 and 5. Then we partial out variable 1, and we ask the oracle, is there a significant correlation, partial correlation in this case, between 3 and 5 given 1? And if we apply the ideas of d-separation and conditioning, we see that if we were to condition on 1, nothing happens to any of the others. There's no collider structure or anything, no chain because it's at the end of a chain. So nothing happens. So true, there is a correlation between 3 and 5 if we condition on variable 1. What happens if we condition on variable 2? Well, that's the same situation. So yes, again, true. Does it change if we condition on variable 4? Again, this is the same because there is no collider structure or anything. Now we come to a more interesting case and we see that we need to condition on 2 variables simultaneously. And if we do this, we condition on 1 and 2 simultaneously, then again, nothing changes between the correlation for 3 and 5. And we can continue this, and we should, doing not only 1 and 2, but also 1 and 4, and 2 and 4. All those combinations should be done, also 1, 2, and 4 simultaneously. And we go through the whole list, and all of them will have changed nothing in the relation or correlation between 3 and 5. It still exists. So we know that there is no set of nodes, any combination of the other nodes will do, such that it takes away or explains away the correlation between 3 and 5. So there must be a connection between 3 and 5. This is what we know because we asked the oracle each time if there was a correlation, and yes, each time for any combination of variables that we condition on, there was a significant correlation. So we know that there's a direct connection. We don't know the direction yet, but we start out with whether there is a connection. Now we move on to another set of nodes and we pick 3 and 4. Now let's see what happens. Is there a correlation between 3 and 4 if we consider the graph, right? We ask the oracle, is there a correlation? And the oracle looks at the graph and says, no, there is no correlation between 3 and 4. Now what happens if we condition on variable 1? Does that change the correlation between 3 and 4? No, it doesn't. It doesn't have any effect like that. Neither for 2, but now if we condition on 5, if you recall, 5 is a collider node. So if we condition there, then according to the Lauritsen rule, we had the situation that we had to marry the parents. 3 and 4 are parents of 5, and they don't have a connection. So what happens is, if we moralize the graph, it means that they are connected. In other words, a correlation will arise if we condition on 5. And so there is suddenly a correlation, a partial correlation, when conditioned on 5. So this is a particular situation, and this is quite unique for a collider situation like this, between the nodes 4, 5, and 3. Now if we go further and we condition on 1 and 2, then we see nothing. But if we go further and we condition on 1, 2, and 5, then we'll see again that there is a correlation. So each time the variable 5 is in the set we condition on, it turns out that there is a correlation. And in all the other cases, there is no correlation. So we know that there is no direct connection because there's no correlation. But anytime we condition on a set of variables that includes the variable 5, then there is a correlation. And so this makes it likely that there should be a collider between 3, 4, and 5. Now let's continue to the variables 1 and 4 because we need to check all pairs of variables, and for each pair of variables we go through the whole list. So we start again with the correlation. We ask the oracle, is there a correlation between 1 and 4? And the oracle says, no, there is no correlation between 1 and 4. Even if we condition on 2, no, still no correlation. What happens if we condition on 3? Well, now it becomes interesting because if we condition on 3, there's a collider there between 2, 3, and 1. So if you condition on 3, we know from the Lauritsen rule that we connect 1 and 2. So there's a connection between 1, 2, and then what happens? Nothing, because we condition on 3, so it goes nowhere. But we did encounter a collider situation. But not always does it turn out to be a significant correlation for the variables we're interested in. Now what happens if we condition on 5? Again, a collider situation. And so we marry 3 and 4 to moralize that part of the graph. And so now suddenly we see that we can go from 1 to 3 and directly to 4. So if we condition on 5, we introduce a connection between 3 and 4. So there opens up a path from 1 to 3 to 4. So there suddenly again a correlation arises. Now if we condition on 3 and 5 again, it disappears again, of course, because because we block the path from 1 to 4 via conditioning on 3. So there's no collider directly from 1, 3, 4. That's what we know, because this only happens when we condition on 5. There's no connection between 1 and 4 because there's no correlation. So that's basically, so those were examples of the inductive causation algorithm by Pearl, and we can write it up in more general terms, of course. And what we put in is a sample distribution. That means that we have measured subjects or observations, and we have made a distribution from that. And that distribution will tell us whether there are conditional independencies, or in our case that we discuss now, we think of them just as correlations and partial correlations. And what we get out of it is an acyclic graph for this distribution. And the first rule that we use is the following. We take a pair of nodes, any pair, and for that pair of nodes, we consider all combinations of other variables that we could partial out. And if it happens that for one of the variables or one set of variables that we partial out, we find that there is an independence, then we know that they are not directly connected because we can explain away this dependence. But if there are no variables in the separating set, and that's what SAB means, the separating set for the variables A, B that we're interested in. If there are no such variables in there, then A and B are dependent. And so we draw an edge between them. Then, after we've done that, for all pairs of variables, so for large graphs, this is a huge number to check. And if we've done that, then we take a triplet or trio for ABC in this case, for any set of variables, and we check to see whether there's a connection between A and C and B, but no connection between A and B. If we then check to see if if the variable C belongs to the separating set for AB, SAB, then if there is such a variable, then we do nothing, right? If C belongs to the separating set, then it must mean either a common cause or a chain from A to B or from B to A. And so C explains away the dependence between A and B. However, if C is not in the separating set, then we have a collider, because it turns out that there's a connection between A and C and between C and B, but no connection between A and B. But it does occur, the connection between A and B, if we condition on C. So it's not a separating set, but there is such a structure where we have two edges with three variables. And so we must make a collider. That's what we know for sure. Of course, this is still depending on the situation where we ask the oracle to see if the connections are really there, or if the partial correlations and correlations are significant or not. And if we've done this for all triplets of variables, then we can orient as many of the undirected edges as possible. But we have to be careful not to make new V structures or collider structures, and we cannot include any new cycles. Because if we do that, then we must have missed something, right? If we introduce new V structures or collider structures, we must have missed it in our first round, which is not possible because we've searched everything. So this is the general idea of the inductive causation algorithm, and it's one of the first to arise, together with the BC algorithm. They are basically the same. And as I said, there are many variations to this, but all of them use the first two rules, and the third also, but there are many variations on how to introduce new versions to get as many undirected edges as directed. Now, we've relied up to so far on the idea that we can just look at partial correlations and correlations and work with that. In general, we need to work with conditional independence relations, which is stronger than correlations. But if we work with multivariate normal data or Gaussian data, then these things are the same. In other words, if we have three variables and they have a multivariate normal distribution, we find that if x and y are independent conditional on z, then they are also conditionally uncorrelated. So the partial correlation is zero. So if they are independent conditionally on z, then they're also uncorrelated. But this is also true in the reverse situation. So if we find a partial correlation of 0 for x and y given z, then they are also conditionally independent. So this is very, very particular to the multivariate normal distribution. Partial correlation implies conditional independence. For no other distribution, for example, if you have binary data with values 0 and 1, 1 and 2, then this does not hold. You need to check for conditional independence, and you cannot rely on correlations. Now you may think, well, all we've done is take a set of variables and consider the correlations. And if we do partial correlations, isn't that the same as doing regressions? And yes, you are correct. This is indeed very similar. So why don't we just do a regression? And there are situations where you could use regression for this, but you don't just use one regression. And I'll show you why that's the case. Suppose we have this true graph and we use the same setup as before. So there's an oracle we can ask whether there's a correlation or not. And he or she gives us the truth. So the regression framework says we have a dependent variable and all of the other variables are the predictors. And this is the picture it looks like. In the regression framework, all of the other variables have a causal relation to y. Possibly. We don't know, of course, for certain. But this is what we believe. And what we now check is basically one regression where we hope to find whether each of the predictors has a significant correlation or scaled correlation, because it's a regression coefficient, with the dependent variable. And we conclude that if there is such a relationship, significant relation, then this must be important. And so there's a correct direct connection of the variable to the dependent variable. And this predictor then is interpreted as being important, directly relevant to the dependent variable. But we'll see that this is not necessarily correct. So suppose we have that network that's on the top, and we ask the question, is there a connection between y and 3? So does y predict y? Does 3 predict y well? And what we interpret is that it's extremely relevant to know 3 in order to predict, and maybe also to manipulate 3 in order to find a change in y. That's our interpretation. Now what happens if we ask the question to the oracle, is there a correlation, a partial correlation between y and 3, given that we condition on 1, 2 and 4? The oracle goes to the graph and then sees that we also condition on 2. What happens if we condition on 2? We introduce a connection between 3 and y. And that's because at 2 there's a collider between 3 and y. And so taking the moralized version, we see that a correlation appears between 3 and y. The other variables are also conditioned on, but they are irrelevant for that connection. So we find that there is indeed a partial correlation between y and 3. And so we conclude from a regression point of view that 3 is important for y, and we may conclude that manipulating variable 3 might lead to a change in y. But of course, looking at the causal graph, we see that this will definitely not be the case, because both 3 and y are causally related to 2. 2 is a common effect of 3 and y. So changing something in 3 will cause a change in 2, but will have no effect on y afterwards. And so the interpretation of the regression in that sense is incorrect. Yes, it may say something about predictability, but nothing further, nothing about a causal relation. In order to do so, we have to check all the possible regressions between y and 3 without any of the other variables, so that's basically the correlation, with one variable out, with 2 variables out, 3, etc., and all combinations, similar as before. And so a single regression will not help us. We need to do a series of regressions, just as we did a series of checks on the correlations and partial correlations. So this is how we get to our data, from our data to a graph. And if we do it incorrectly, just by a single regression, then we won't get there. We need to verify all combinations of partial correlations, or all regressions that we can think of, for all combinations of variables. That will allow us to get from the data to a graph.